I'm going to talk about what it means to be just in time. My name is Ashley Puls. I am a senior software engineer at NewRelic in Portland. NewRelic is a company, it's a software analytics company that makes sense of billions of metrics across millions of applications. And I work on our Java agent team, so that is the team responsible for extracting metrics out of Java applications, and then we send them up to our infrastructure and you log in and see your performance data in our UI. So generally that means that I work a little bit above the compiler level, but a little bit below the application level. We do have a license agreement, and now let's get started. How many of you have made that catch just in time? You know, you felt really good about yourself. Or we had the World Cup this summer, you made that save, the other team didn't score the goal, yeah. What about the other side? How many of you wish you would have been there just in time, a little bit earlier? So today I'm talking to you about the just-in-time compiler. Most of us, we write Java or some language that runs on the JVM. We compile that code using Java-C down to bytecode, looks something like this. And the bytecode is the language that is run in the JVM. Also in the JVM is the JIT compiler. This chooses specific methods to compile down to machine code. So notice we have two compilers here on our stack. We have Java-C, which is a static compiler, and then we have the JIT, which is a dynamic compiler. I like to think of Java-C as those days when you had those paper maps. Do people actually remember those days? You had to actually print out the map or use the book to get from point A to point B, right? Once the paper is printed, if there's a new road created, you don't see it on your map and you don't use that. That's a little bit like Java-C. Now today, most of us, you need to get from point A to point B. You take out your phone, you pull up some maps application, and it gives you directions on how to get there. Likely, this program is updating based on traffic or construction or road closures, etc. So it's very dynamic. It's getting updated on the fly. And this is similar to the JIT compiler. The JIT compiler gets to use all of the information available at runtime to figure out what it should optimize. Now, there's actually a little more going on here in the JVM. One, we have an interpreter. The interpreter is what first starts off reading and executing your bytes. And the interpreter in the JVM is actually pretty intelligent. It's a template-based interpreter. So what does that mean? Well, it essentially means that there's these templates, and I like to think of templates as a mapping from essentially your bytecode to the assembly code for that bytecode. And all those templates, they live in a template table. And so what's happening is there's actually assembly code being executed, even in the interpreter. So this is fast, but it's also pretty complex. And it requires assembly code to be generated for all the different OS and hardware systems. So it does require a lot of space. Now, if you're interested, you can actually go and see all of the assembly code that's in these templates by using the print interpreter flag. And it'll print out and it'll look something like this. So you'll see your iStore and then the assembly code for that. Next, we have our profiler. Our profiler collects and aggregates profiles. And a profile is information which summarizes the behavior of a bytecode instruction at some profile point in the program. So essentially, in these bytecode instructions, they're profile points, and they're gaining information. And this allows the compiler to then make transformations, and the transformations are going to occur at the method level. So what are some examples? Well, perhaps you have a null check. The profiler is going to record whether or not it's actually ever seen a null at that null check. Or if you have a call site and there's different types, it's going to record how many types it's actually seen. And it's actually only going to really record if it's seen one type or two type or more. And then it's going to keep execution counts. So how many times has this method been called? How many times has this branch point been called, et cetera. And the goal of this profiling data is to really determine what methods should we optimize. And the JIT compiler is there to optimize, and there's actually several modes of compilation. One of them is the client mode, also called C1. This was designed for clients. And so it's really run in short-running JVMs or GUI-type applications. It starts up very fast, but it only performs basic optimizations. Next, we have the server mode. I would guess a lot of you, if you have servers, you probably run in this mode. Yes? No? It has a slower startup, but it aggressively optimizes, and it's designed for long-running JVMs. And then nowadays, starting in Java 7, there's the tiered compilation mode. And this is designed to be the best of both worlds. You start in a C1 type environment, and then you move to a C2 type environment. And if you're running in Java 8 and you're using the default compilation mode, this is what you're getting, tiered compilation. So the compiler chooses the method based on the profiling data and determines which methods to turn into machine code. And it makes educated guesses. And sometimes it guesses wrong. And in these cases, it needs to perform a de-optimization. So what it does is it marks the compiled code as invalid, tells no one else to use it, and then once no one else is using that code, can go and be garbage collecting. So this is the de-optimization process. Examples of this is if you had that null check and you've never seen a null before, and then suddenly you see a null. Or you have a cast of a certain type, and suddenly you see another type. Also, class loader a class that's loaded that invalidates an earlier class hierarchy analysis. Now, the reason that the JVM can be so successful with this is it operates on the Pareto principle that says 80% of the time, 20% of the code is going to be executed. So therefore, if the JVM can just figure out what that 20% of the code is and spend its time optimizing that, then it will be able to get your application running pretty quickly. And I think the JVM's really seeing a rebirth these days. If you go to Wikipedia and you look at all the languages that have been created to run on the JVM, there's quite a few. And I think a lot of it has to do with the JIT and the fact that it does and performs all these optimizations. Now, I'm of the mindset that you should always trust but verify. So we should really verify that the JIT's actually going to do something for us. And I'm going to do that by using JMH, Java Microbenchmark Harness. Now, how many people have used this before? Just a few. This is one of my favorite tools. It is a micro-benchmarking framework. So that comes with all the caveats of micro-benchmarking. Be careful what you're actually benchmarking. Think about your results. Are they actually valid? Don't just trust your numbers blindly. This one was developed by Alexei, who's a core contributor of the JIT, and so I like to think that he knows what he's doing. And its setup is pretty similar to JUnit. So when you run JUnit, you have this test file, and it tests your actual code in the application. When you use JMH, you have this benchmark file, and you call into your methods in your application. And for JUnit, you have the @test annotation. Here, you have the @benchmark annotation. So one thing I should point out, since I do work for a performance company, should I really be talking about another performance tool? Well, these actually serve two very different purposes, right? JMH is a micro-benchmarking framework. So it's for looking at small chunks of code and seeing how they perform. NewRelic is an application performance monitoring tool. So that's designed to run in production and monitor your app. So they really don't operate in the same space. Now for JMH, you have a main method, and you have your options builder, which is where you configure how you want your tests to run. And one of the options that I want to point out is the warm-up. Now, we just talked about how there's this whole profiling period where it needs to gain some data before it can do optimizations. So you want all of that profiling to occur in your warm-up. So make sure that you have a good warm-up time period before you actually start doing your measurements. Then at the bottom here, we have the run method, which actually runs your tests. And then there's the for loop printing out the results. This pretty much comes directly from the examples from JMH. So what I have here is my first benchmark. I have the @benchmark annotation at the top there. And I'm saying report my results in nanoseconds. And then I'm just basically doing some work. It doesn't really matter what the work is for this. We just really want to compare with the JIT and without the JIT. I also want to point out that I'm passing in this black hole. So the black hole is designed to help you, you pass results to it that you don't really, I mean, you want all the work to be there and you want the work to be in the benchmark, but you want to make sure that the JIT's not going to optimize out that work. And so what you do is you just pass your results to the black hole. That ensures that the code and the work won't get optimized away. So now I'm going to run, and I'm going to run this benchmark twice. On the left, I have it set up to run with the JIT on. On the right, I have it set up to run with the JIT off. And you can actually disable the JIT for any JVM process. You just pass in the -d java.compile equals none, and that will turn off the JIT. And sure enough, this shouldn't be a big surprise. The JIT enabled runs significantly faster than the JIT disabled. And the numbers here don't really matter. We're just trying to see the comparison of JIT enabled to just disabled. All right, so why should you care, right? Why are you here today listening to me talk? Well, one, I think it's important to have a basic understanding of everything on your stack. And if you're running on the JVM, then the JIT is essentially on your stack. And so you should have a basic concept of what it does. Two, eventually there's likely to be a problem, and I think it's good to have the tool set to be able to debug into the JVM layer and see what's going on. And that's kind of where I'm going to focus today, is I want you to be able to leave today and debug into the JIT and the JVM layers and see what's happening with your code. Now, I tried to come up with a good analogy for the JIT, and the best I could come up with is parenting. I don't actually have kids myself, but I'm told that there's this feedback loop, right? You can think of your kid as your application, and ultimately, you want it to perform as best as possible. And you try something, and it might not work. The kid doesn't really get it, so you try something else, right? There's this feedback loop, so it's a very dynamic process. And so ultimately, you're trying to optimize to get your kid to perform as best as possible. So what I've done is I've created a Spring Boot application, and it's going to represent two children. One is John here. You can curl John, and he'll say, "My name is John. I'm 2." And John knows what his favorite animal is. It happens to be the turtle today. And he knows that the turtle is not a very fast animal. Now I have Sarah. Sarah's 5, and she's working on her addition. Now I don't know, actually. Does 5-year-olds, is that when you start learning addition? Anyone? And multiplication? OK. So I'm roughly accurate here. And Sarah's also old enough to go gather up all the dogs and bring them to us. Now this is your basic Spring Boot application. I'm using servlets here. I have my kid controller. I'm auto-Ying my 2-year-old with my hello John, get animal, and is animal fast method. Then I have my 5-year-old auto-wiring that up too. Sarah, she can do some addition and she can go get the dogs. Now, first thing I'm going to do is run with this flag called print compilation, and I pass that in as a JVM argument to my Spring Boot application. And what this does is it's going to give you some information on what classes are being compiled and what ones are being de-optimized. So you run this, and you will start seeing this get scrolled down your screen. Right? You won't even have your application started yet, and this will just be scrolling and scrolling and scrolling. So what in the world does all this mean? Well, first here, we have the time of compilation relative to the JVM start in milliseconds. Then every compilation gets an ID. Now, the percentage here is on-stack replacement. Who knows what on-stack replacement is? Anyone? No. You're all going to learn something today. So essentially, we have methods, right, that have long-running loops in them. And when the interpreter is running one of these methods with the long-running loops, it will identify that method as hot. And so it'll compile that method, and that compilation will be there, sitting there ready next time for the method to run. However, we're in this long-running loop, so the method's not exiting, so we're not calling it again. So eventually, on-stack replacement is going to be called or triggered by the interpreter, and it's going to do a compilation, and it's actually going to replace what the code it's running right now and there with this new compilation code. So it's doing it right on the stack while the method's running. I think this is pretty cool. It's pretty impressive. Next, the exclamation mark marks exception handlers. So exception handlers have to be handled specially, right? They need the ability to unroll the stack and get the stack trace. The N represents native methods. Then we have the method the JIT is acting on. So most of the time, this is the method being compiled or the method being uncompiled. We have the size of the method. And then here we have this nice column. I like the make zombies. I think that's kind of entertaining. But first here we have the make non-entrant. So what this says is it invalidates the compilation. So it's saying I made a mistake. This isn't exactly the compilation that I want. Please stop using it. And then you become a zombie when no one's using you anymore. And so this says, OK, you can garbage collect this. Now this provides some basic compilation information. It's fun to see stuff scrolling down your screen, but diagnostically, I actually don't find this information very helpful. It'll tell you if your method's being compiled or not, but that's about it. So I think ultimately, to really solve problems in the JVM layer, you have to go a little deeper. So I was working with Sarah on her addition, get doubles, and it started getting really slow. And I brought up, I would expect it just to call add two doubles and add the doubles together and then return that value. So what do I do? Well, one, I go and I write a benchmark. And this allows me to look at the code isolated. And one of the great things with JMH is it does that warm-up period for you. And it'll call your method over and over and over again so you can get the optimizations in there. So I like to use this to just analyze a specific piece of code. Now, the JIT performs several different optimizations, and one of the ones that most people have probably heard about is inlining, right? When you have a small method, generally what the JIT will do is it will actually inline that method. So here on the left, you see the beforehand where we have the add two doubles method, and our test inlining benchmark is calling add two doubles. And then on the right, you see what we expect after the method has been compiled. We expect there to be no call to add two doubles. Instead, we expect a direct addition from A double and B double. So the first thing we can do is we can actually go look at the bytecode. To look at bytecode, you run Java P. When you add the -C flag, it'll actually print out all the bytecode in the method itself. And this is what we see. This invoke special line here is the call to add two doubles. So this here, we know that Java C is not doing any inlining optimization for us. So now we go back to our main method, and we can add some JVM arguments here. And the one I'm going to add right now is print inlining. And this is going to give you more information on inlining specifically. And anytime you use this flag, you also have to use the unlock diagnostic VM options flag. I'm not sure why they tie those together like that, but they do. And once again, you will get a lot of information scrolled to your screen. And so let's go over this. Here, this is saying that this method, number of leading zeros, is an intrinsic, and it's handled specially by the compiler. And then here we're seeing inline hot. So this means that this method is actually getting inlined. Here we're seeing these two methods are too big. So what does that mean? That means that if the method size is too big, then the method itself is not going to be inlined. And this isn't necessarily a problem yet, unless you see what we're going to see here, which is hot method too big. So now we have a method that's being called a lot of times, and it's too big to be inlined, right? So the inlining flag here is providing you lots of information. Every line does not mean that it's something the JIT wants to inline. It's just giving you information. But generally, when you see hot, that means it's something it wants to inline. Now here we see our add two doubles method, and we see callee too large. And if we scroll down more, we see hot method too big. So this is bad. Our add two doubles, for some reason, is not getting inlined. So I went back to Sarah and I said, Sarah, what are you doing when you're adding these two doubles together? And Sarah explains to me, she says, well, I'm singing Mary Had a Little Lamb a couple times before I do the addition. And so this is why I'm getting so many bytes in my method, and it's not able to get inlined. So I tell Sarah, stop singing Mary Had a Little Lamb before you do your addition. Come on, that's supposed to be funny. You all are supposed to laugh. Ha, ha, ha. Thanks. I'll take the pity laugh. All right, so we've told Sarah no more Mary Had a Little Lamb. So we have the before and the after. So now, since we have, we're learning how to do this debugging, I think we should go verify that the method does actually get inline when it's just the two additions. So we rerun the code. And sure enough, we see add two doubles inlined hot. So we know it's now being inlined. So this pretty much has, we figured out our issues here. But if we wanted to dive deeper, we could go and print the assembly to system.out. And one thing about printing assembly, you can't just add the PrintAssembly flag as a JVM argument. You do need to install the hotspot disassembler, and up in the right corner there, if you go to that link, they have pretty good instructions on how to do that. So now you're going to see assemblies scrolling down your screen, and I encourage you to take a deep breath, and I think everyone can look at this and understand what it's saying. So here we have our test inline method. This is getting printing out after a compilation. We have a bunch of registers. So we see here on this line, the A double is being moved to MM0. And then we see B double being moved to MM1. And then we see the addition happening, and the result is being put in MM1. And then down here is the call. That's the call to the black hole to consume the result, the 12.1. So what we're seeing here is we're seeing a direct add. If there was a call to add two doubles, we would see another call line like this for add two doubles, but we don't. We just see the one for the consume method. So we know, in fact, that our method is getting inlined. Now yes? I'm not exactly sure. My guess is that that is setting the memory in the right place. Yeah. So if you don't, I like grepping logs, but if you're more of a GUI type person, there is a tool out there called JITWatch that will read your logs for you and give you some nice graphs. This is one of the graphs it'll do. You can see the method test inlining calls add two doubles and consume. We can see that consume is compiled, but not inlined. And then we can see that add two doubles, based on the key on the right, is compiled and inlined. So this is nice. You don't have to go to the logs, et cetera. One of the other graphs I like in JITWatch is this is giving you the count of compilation, and you can see when your method was compiled, but more importantly, you can see when the graph is leveling off to know that pretty much most of your compilations have occurred. Now, one other thing you can do in JMH with inlining is they have this compiler control option, and you can set it to not do inlining. So all the other JIT optimizations are occurring, but it's not inlining. And when you run that, you do see that there is a performance difference between inlining and no inlining. So the average there, you're getting about 14 nanoseconds when you're inlining the method, and 20 nanoseconds when you're not inlining the method. So what have we done here? We have actually looked at the Java, the bytecode, and the assembly language for our code. We saw that we had our method add two doubles in the Java. We saw that that call with the invoke special was still there in the bytecode. And then in the assembly, that's where we saw that it got optimized away. So when you're doing your diagnosing, set up a JMH benchmark to isolate the code. Use Java P to examine the bytecode. You can use the print inlining flag or the print assembly flag, and then also know that the compiler control modes are there for you too. All right, so we fixed the method. It's running a lot faster. That's good. And then suddenly it gets slow again. So this time I'm just going to ask Sarah, what are you doing before you do your addition? And Sarah says, well, I like to practice my addition, so I'm adding 1 plus 1, then I'm adding 2 plus 2, and then I'm doing the addition that you want me to do, which is 1 plus 2. So this is a good time to talk about dead code elimination. So I can write another benchmark, test dead code. I have a value that's not being used at all, and then I have another value that is being consumed. So what I expect to happen is I have my before, which has the value of AW plus pi, and then I have my after. That code should just be taken out. The JIT should optimize it away and not do that work. So I can go back to Java P, look at my bytecode. Sure enough, the code is still here. Java P is not optimizing this away. And then I can go run with that PrintAssembly flag again, pull up my test dead code optimization, and I can see here I have a double, and then it's getting added. This is all being done in an MM0 register. And then here I'm seeing the B double work. And then I'm seeing, but the bottom line here, the results kind of being consumed. Now that's the first optimization. So the A double addition is still in there. So then I see that the method gets optimized a second time. And here I only see one add. So the A double has been removed. We just have the B double now. One other thing I can do to test this is I can run 2 benchmarks. One where the value is not used here on the left. And on the right, I'm going to consume that AW plus phi value. So now I'm using the results. And what happens when I do this? Well, I see that it takes 2 nanoseconds on the left and 4 nanoseconds on the right. So that also leads me to believe that the code on the left is being optimized and the value, the AW plus pi, is not occurring. All right, so once again, we've looked at the Java, the bytecode, and the assembly language. And we saw that it was the JIT compiler who did the dead code removal optimization. And our steps for doing this, we wrote a JMH benchmark, we looked at Java P, and we used the PrintAssembly flag. So things are good for a little while again, and once again, A double, or get double, gets slow. So I asked Sarah again, what are you doing? She says, well, I'm creating a pairs class where I have my value 1 and my value 2, and I has a sum method. And what I was doing is I was creating a new pairs, and then I was calling sum on it. But now what I'm doing is I'm putting a public pairs P as an instance variable, and then I'm creating my new pairs in my test, and then I'm calling sum. So does anyone know what this optimization is? We have the before. This is called escape analysis. It's right there in the method name. And essentially what escape analysis does is it looks at the scope of your variables. So on the before here, pairs is scoped to the method. But on the after, pairs is public instance variable, right? So anyone can see it. So on the before case, the JVM can actually say, well, I don't actually really need to create this pairs object. It's not ever leaving this method. But in the after case, it has to create the pairs object. And that's an object, right? So it's going to go into the heap. And you have all the overhead of the heap. So one thing you can do to test this and see the difference is actually to look at your garbage collection. There's not really a great flag for escape analysis. Well, there is one, but you have to run with a debug version of the JDK. So if you're using a production version of the JDK, there's not really any great flags out there. So what I'm going to do is I'm actually going to add a profiler, the garbage collection profiler, to my JMH, and I'm going to make my memory very small, so I should be garbage collection quite a bit here if there's any garbage there. And then I'm going to run both of my tests. And here's my results. So on the before, I see that there's no garbage collection. Nothing's going into the heap. But after, I see that there's a whole bunch of garbage collection running. And also look at these times. So on the before, I was around 2 nanoseconds. And after, I'm around 5.5 nanoseconds. And this is just by taking that pairs, my Java code, I'm creating the new pairs object. The only difference is, right, the scope. The scope of the before is the pairs is constrained to the method. And after, the scope is everyone can see it. And so here you can see the counts. We see 0 on the left, and we see 5,500 there on the right. So this actually makes a pretty big difference. So the lesson here is really be careful about how you're scoping your variables and keep the scope as small as necessary. We can also look at the bytecode. Here's the before. So here you're seeing the add there. And here after, you have to create, you see the new, so you're creating the pairs object. And then the before, that's not there. All right. So here, what have we done? We've written a JMH benchmark. We looked at the GC profiler. And we also looked at the assembly, the print assembly. And we go back to Sarah. We tell her reduce scope whenever possible. All right. Sarah is getting a little tired doing addition. So we're going to move on to John. Now, John, I asked him over and over again, John, what is your favorite animal? Is your animal fast? And John replies, turtle. No. Ask him again, what's your favorite animal? Turtle. Is it fast? No. Ask him that several times, and eventually I ask him, and he gets much slower, and he says, tiger. Say, is your animal fast? Yes. So this slowness is something that's very similar, actually, to what happens in the JVM. We can create our animal, and we'll make it an abstract class with our isFast and our getName method. Now we can have our turtle. We know our turtle's not fast, and our name of our turtle is turtle. Now we can write a benchmark. So what am I doing here? I have my current animal is a turtle. And I'm consuming the turtle getName and turtle fast. And I'm doing that 5 billion times, I think that is. And after 5 billion times, I'm swapping out the turtle and putting in my tiger. Now what happens? So here I see I have a system out just to tell when my tiger's there. And I see that I go from about 5.5 nanoseconds up to about 6.5 nanoseconds. And I stay at that 6.5 nanosecond level after the tiger is introduced. I don't go back down. So maybe the tiger is just actually slower than the turtle. So I can swap this. I can start with my tiger, and then after 5 billion rounds, switch to the turtle. What happens? The exact same thing, right? I'm roughly around 5.5, and I go up to more like 6.5 after the turtle has been introduced. So it's not about the turtle or the tiger being faster or slower. It seems about having one animal object versus 2 animal objects. What I'm going to do here is I'm going to do the print assembly flag and the log compilation flag. We've seen what the print assembly flag does. It prints out a whole bunch of assembly code. The log compilation flag prints out a whole bunch of messy XML for you. And this is where it could be good to use JIT-watch. It parses all this XML. And it prints it out to a hotspot log. It typically has the process ID in it, too. And what you see is you see first that there's a queued up compilation for our method, test polymorphism, and we see our compiler ID 279. And then we see the method actually getting compiled. And we can see that it first gets compiled with C1. Recall our 3 modes of compilation. C1 is client mode, C2 server mode, and the tiered compilation. And I'm running with Java 8 here, so I'm using the tiered compilation mode, the default. So I'm starting with C1, and I should see it move to C2. So next, I see another compilation get queued up here, and this ID is 285. And I see that compilation actually happen. And sure enough, I see it's compiled with C2. Next, I see this make not entrant. And if you remember from when we first were looking at the logs, this is saying don't use that initial compilation anymore, the 279. We want to use the 285 now. And next, I see something new, an uncommon trap. And the reason is a class check. So what's happening here is the JIT has assumed that when we have an animal, it's going to be a turtle. And suddenly, it's not seeing a turtle anymore. It's seeing a tiger. So what it's doing, right there, the uncommon trap, and the reason the class check. So it's saying, don't use that 285 that we just compiled. Go back, use the interpreter mode. I think I've made a mistake. And then, sure enough, we see another compilation go into effect. So optimization 1. Here we see the call to get name. And this is the call to get name on the animal, right? So this is basic. We haven't really seen anything about the turtle yet. Now we go to optimization 2. Here we're seeing a comparison for getTurtle. So for turtle, we're going to do some special logic. If not, then we're going to jump to this location, the E99 there. And we can go down to that E99, and we see the get name call there. So we're going back to looking at the general animal again. Optimization 3. So here we see the compare to the turtle. And if not, then jump to the 7848 there. We can jump to the 7848, and what do we see? Well, now we see a comparison of the tiger. So we've optimized for both the turtle and the tiger. And if we jump to that one, then we get the animal get name call, right? So typically, the JVM will optimize for 1 or 2 different types. But if you have more types, it's not going to optimize. And we can go ahead and verify this. So now I'm going to add in a buffalo. And I run my test. And here I see, so I go from about 5 nanoseconds up to 6.5 nanoseconds when I change from a turtle to a tiger. And then when I change from a tiger to a buffalo, I go from about 5.5, 6 to up to 8 there. Right? So once I have 3 animals, I've lost this optimization. And just to verify, am I going to keep increasing for every animal I add? I'm going to add a tiger, a buffalo, a giraffe, a bear, and a turtle. Now I go ahead and run this. So I see my time increase from when I go from turtle to tiger. I see my time increase from when I go to tiger to buffalo. And I do not see any increase from when I go to buffalo to giraffe. And nor do I see an increase from when I go to giraffe to bear, right? So this is showing that the JIT's optimizing for 1 type and 2 type and not 3 or more types. All right, so this is polymorphism. Essentially what I've done is I've sent up a JMH benchmark, and I ran with the print assembly and the log compilation. And so the case when you only have 1 type is called monomorphic. When you have 2 types, bimorphic. 3+ types is megamorphic. And what we learned today is essentially the less types you have, the faster you're running with for 1 or 2. So what do we go and tell John? Only 1 favorite animal. Don't be switching to the tiger. OK, so we've looked at a lot of assembly today. One thing I've glossed over a little bit are these test lines. Does anyone know what these test lines are here for? Yes? Sort of. Yes, you're on the right track. They are Safepoint checks, which can be garbage collection. And so what I'm going to talk to you about next is Safepoints. And the reason they relate to the JIT is that the JIT is responsible for putting in these Safepoint checks into compiled code. So if you're in interpreter mode, the interpreter dispatch table is changed to force a Safepoint check whenever you need to do a VM method But in compiled mode, it's the JIT who's responsible for putting these test lines in the assembly code to ensure that the VM still has time to run its operations, right? Because the JVM is essentially just a VM, and ultimately it needs to do some work every once in a while. And the way that that is done is through Safepoints. So my analogy here is when I tell Sarah to go get the dogs, suddenly it takes a lot longer. And I recall that, oh, I just went and bought a few more puppies, because that's something clearly we all do every day. It takes a lot longer. And so this is similar to your threads, right? Each puppy is a thread, and the more threads you have, potentially, the longer it's going to take to run a Safepoint. Why is this? In compiled mode, you have your threads and your Safepoint checks that happen. When a Safepoint check happens, so when we get to one of those test lines, what happens is the JVM goes and checks a specific page in memory. It reads that specific page. And if the page is present, great. There's no Safepoint, no VM operation needs to occur right now, and the thread can continue on its way. When a VM operation, like garbage collection, needs to happen, the JVM removes that page. So the thread tries to read the page, or I should say it removes read permission on the page. So when the thread goes and tries to read that page, it's not there. It throws an exception. The JVM can catch that exception and keep that thread right there. Now that thread has to wait for all the rest of the threads to reach a Safepoint check, to go read the page, and to throw the exception and be caught. So we see thread 2, and then we have to wait for thread 3. Now all of our threads are in this Safepoint mode. So now the JVM knows that it's safe for the VM thread to run and do whatever VM operation it wants to run. Now there's actually, most people think of garbage collection when they think of Safepoints, but there's actually a lot of VM operations. It's not just garbage collection, class redefinition, getting stack traces, heap dumps, de-optimizations, which we've talked about, print threads, get all stack traces, etc. So all of these operations require a Safepoint to occur. All right, so let's write a few benchmarks here and examine Safepoints. This one's a simple one. It's taking two integers and just adding them together. To get Safepoint information, I'm first going to run with the hotspot runtime profiler. This is going to print out results like this. So at the top, I get my timing information. This very simple benchmark is taking a little over 2 nanoseconds. My Safepoint sync time is essentially nothing. Safepoint time is essentially nothing, and I'm hitting 5 Safepoints through the duration of the entire test. So really not many. Now I'm going to change my benchmark to do a thread get all stack traces. And what I see now is I see that I have definitely doing a lot more Safepoint hits, right? Because get all stack traces is something that requires a Safepoint because it needs to go to all the threads and get their stack traces. And when you're at a Safepoint, that's the one time when you can be guaranteed to touch the memory of all the threads because none of the threads are modifying their memory because they're all in this Safepoint mode. So I ran this test. I ran it with 1 thread, 10 threads, 20 threads, and 30 threads. And I see that the average time of my benchmark goes way up as I increase the number of threads. This is something I expect. As I'm increasing the number of threads, that's more threads that have to get to this Safepoint. So I expect my time to go down. Now, if you look at the column far to the, I guess that's your right, the Safepoint count, this is something I was not expecting. When I have 1 thread, I hit way more Safepoints than when I have 30 threads. So why is this? Well, first I wanted to confirm that this hotspot profiler that's running in JMH is actually giving me the right results. So I'm going to do the JVM flags just to verify the results are the same. And that's this print Safepoint Statistics and the print Safepoint Statistics count. This is going to print out a whole bunch of information. On the left here, I get the time along with the VM operation that was run. Then I get a whole bunch of information on the threads, so the number of threads stopped, number of threads initially running, number of threads blocked, etc., and a bunch of timing information. Then I also get this summary at the end of all of the safe points, the VM operations that ran. So the majority of them are a thread dump. When you call that get all stack traces method, that's what's happening. It needs to run that thread dump VM operation. And sure enough, these numbers are pretty much the same as what I got through using the profiler through JMH. So the JMH is giving me the same result as the JVM. So let's go back and look at our test. Here I see that the benchmark mode is average time. So what does this mean? Well, it means run the test as many times as you can per an iteration, where an iteration is a unit of time. So what I'm actually seeing happening is my throughput is decreasing enough that I'm hitting significantly less safe points. This makes sense. So what I can do is I can change this to single shot time. So this runs the benchmark once. So when you run in single shot time mode, you want to make sure that you have a long warm-up period, right? Because you're only running the test once. And now I get information that is more like I would expect. I see the number of safe points increase as I increase my threads. So the real thing to think about here, yeah. I'm defining the safe point count as the number of times that you need to run a VM operation. So you actually need to safe point, not check the page, but have the page not be there. So this is the data that we would expect. Now, one other test that you can run, which I don't have shown here, is you can do a thread, get a thread, specific thread, another thread that's not you, and get its stack trace. Now, do you think that this is going to require a safe point? Anyone? The answer is yes. So even though you're only wanting to get the information from one other thread, you want its stack trace, you actually still have to run a safe point. You have to hit a safe point and do that stack trace method. And if you think about how this is all set up, that makes sense, right? Because there's only one page that gets removed. There's not a page for each thread to go read, but there's one page in general. And so you can't say, OK, this one thread, you need to stop and I need to get your stack trace. You have to remove the whole page, have all the threads come to the safe point, and then get that one thread stack trace. So this is a big pain, I find. But if you think about how it's actually implemented, it really does make sense. So the one question here that I think a lot of people don't really actually think about, but is really important, is how long are my threads sitting idle waiting for all the other threads to reach a safe point, right? If you're running a JVM with thousands of threads and you want to go get a stack trace of one other thread, you now have to stop all of those thousands of threads. And the one might hit a safe point check. And now you're waiting for the next one, the next one, the next one, right? Until all of these like 5,000 threads stop. So one thing you can turn on to check that is the print GC application stop time argument. And if you look at your logs, now you'll see these statements, total time for which application threads were stopped and the amount of time in seconds. So one other thing to talk about here with safe points is that there's certain methods that cannot have safe point checks in them. A good example is arrays copy. So we can write a benchmark where we have this large array, I think it's 200 billion, and I'm initializing it in the main. And then my test here is going to copy that array. I think it's 115 million positions. And then it's going to go get all stack traces. So here we see the initialization, and here we see the copy. Now what happens? Well, here's our base case with no copies. Now we have our 15 million, so the min is pretty much the same. The average, we're already starting to see a significant difference. We've gone from less than a millisecond to 62 milliseconds by just adding this array copy in. And if you look at like the 99th percentile, we've gone from less than a millisecond to 392 milliseconds. So this is a significant amount of time, right? Like just by adding in this array copy, we are significantly increasing our time to Safepoint. Okay, so now you might say, well, 15 million objects, that's a lot to copy. So why don't we do something just like 150,000? So the min is very similar. The average is just a little bit more. And if we look at like the 99th percentile, we're seeing a couple milliseconds difference, right? And this is the time to Safepoint. So this is how long are my threads waiting for all the other threads to get to a Safepoint. This is not the time of the whole test, but the time to Safepoint. So this is something definitely to keep your eye on. So what have we done here for Safepoints? We've set up a JMH benchmark. We've used the JMH hotspot runtime profiler for Safepoint Statistics. We also used the JVM flags, print Safepoint Statistics and print Safepoint Statistics count. We changed from average mode to single shot mode. And we used the print GC application stop time to print some timing information. So the key takeaways and the key things to think about here are 1, what is your time to Safepoint? And 2, how many Safepoints are you introducing into your code? All right, so I tried to curl Sarah and I tried to curl John. Neither of them are answering. I think they've fallen asleep. So I think it's time to go over a summary. So debugging the JIT. What are the steps you want to take for debugging? Well, 1, you want to make sure that you warm up the system. And I like to use JMH. I think it's a very easy tool to use to do this. Then there's a whole slew of JVM arguments that are out there that are available for you to see various types of information, whether it's inlining, whether it's the assembly code or all the compilations. And so I encourage you to go and use these to look at what's happening in your JVM. And don't be afraid to actually read the bytecode and the assembly code and see what is actually being executed. So my key takeaways here. We've talked a lot today about optimizations. And you might want to go back and run all these flags on your application and start changing your code, get rid of all these types and stuff. But I want to remind you that you don't want to optimize until ultimately it is deemed necessary, right? Most of our JVMs today are network bound. They're not CPU bound. And these type of things really only come into play when you're in a CPU bound environment. So really, you can go have lots of fun and take out your types and check your if-else statements. But you're probably not going to get a huge performance gain unless you're ultimately CPU bound in that JVM. So don't just optimize just to optimize. Now know how to debug into the JVM layer. And this is what I've tried to really help you out with today. And hopefully when you go home tonight, you can actually, if you have a problem in your JVM layer, debug into it and figure out exactly what is happening. And there, I've only covered a few JIT optimizations today, right? I covered inlining, dead code removal, polymorphism, and escape analysis. There's a whole bunch more optimizations out there that I have not covered. And part of the reason I decided not to cover all of them today is that I think it's very easy for you to just go read them online somewhere. But to be able to go debug into your system when you have a problem, I think that's really important. And I hope you will remember these flags and use them when you need them. Third, keep an eye on your time to Safepoint. So a lot of people get very focused on garbage collection, and garbage collection is a huge problem in a lot of JVMs. But I also think that this is a problem that a lot of people are not aware of. And so I encourage you to go check your time to Safepoints in your JVM applications. Next, go learn more about the JIT. It may help your parenting. And the JIT is designed to optimize simple code. And so ultimately, at the end of the day, you should really just try to write simple code. If you write simple code that the JIT is expecting, then it's going to perform the optimizations that one would expect, and you're going to have a decent runtime performance. All right, so I've talked really fast today, and that's pretty much all I have. I work for NewRelic. We are hiring. And any questions? Yes? Oh, the escape analysis example. Correct. So the question was, on the pairs example, this escape analysis, did I say that the object was not being put on the heap? And the answer is yes. If we pull up the bytecode, what's happening is that the pairs object is actually never even being created. The JVM is saying, I don't need to create this object. I can perform optimizations to not even have to create it so that it doesn't have to go in the heap. And if I find the bytecode, I think, shows this. Yeah, so here you can just see, it's like the fourth line down, there's the add. So it's doing the addition, but it's never actually creating the pairs object. There's no new creation there. But if you look at the after, when we have the pairs object as a public instance variable, you do see that it has to create the new, it has to add in the, the 1 and the 2 are getting moved over, and then it's doing the addition. So in this case, because it's creating the pairs object, the object's being put in the heap. And that's why I can look at garbage collection in this case, is because essentially what I'm seeing is the object being created or is it not? Yes? Sorry, can you speak a little louder? So the question was, this is when you have the decompile flag, right? So you see the assembly code, you have to add the disassembler jar to your tools directory of your JDK. You don't need a full debug JDK in this case. There is, I forget the name of the flag, but there is an escape analysis debug flag. And to run with that, you do need a debug JDK. But here, just to get the assembly code, you need the disassembler jar and put it in your tools directory. Yes?
So one of the challenges we have with anything related to performance tuning is that it falls into the 1% of workflows that typical engineers are going to follow. It's just, we write code. Do you have any tips or any practices that you see that kind of walk people, like a refresher every time, oh, I'm getting in here in my 1 month agile cycle, I have a problem, and I need to think. Do you have any sort of workflow or recommendations?
Yeah. So the question was, do I have any basically workflow or recommendations about performance, right? So at NewRelic, we run in all sorts of different environments, and we have to be very performance conscious because we're running in production environments. And so we just basically make it part of any task that there's a performance component. We use JMH extensively. We have a whole slew of JMH tests that get run. And when you're doing a feature, just part of the time for that is to write your JMH tests and also do a higher level application kind of running test and verify that you're not hindering or increasing the time or overhead. And we run our JMH tests once you add new ones for new features. We run them every day. And check to see if there's any increase in performance. So really, I think it's just about keeping a performance focus. I really like JMH. It's great for us because we're running in so many different environments. We do have a whole suite of applications that we run our code on. But to really see if we're introducing any type of like Safepoint or anything like that, the JMH benchmarks really help out. And things like get stack traces, right? That's something that's we're very conscious about because that's the type of information that we're trying to pull too. So I think it's just about making sure you have a focus on performance and putting it in all of your projects. Yes?
So the JMH results, they are tied to the hardware?
So are the JMH results tied to the hardware? I mean, yes, essentially, right? Because ultimately, the JIT is going down to assembly code, and that assembly code is going to be tied to the hardware. So yes, be conscious. I run all of these JMH tests just on my MacBook because ultimately here is more about seeing what's happening. But like for us, we run our JMH tests on like Linux boxes because that's what most people use.
So in our case, like my production box will have just like even 12 ports, right? My developer usually has 4 ports. So the JIT would take like different decisions based on this different configuration.
I mean, it's more, so the question was, like, does the cores really matter, right? And so I would say it's more about, are you running an Intel chip? Are you running AMD, et cetera? Are you 32-bit, 64-bit? And what's the assembly code that the JVM's putting out there for you, than necessarily memory. I mean, memory is going to impact things like how frequently is your garbage collection running. So ultimately, you want to try to mimic your production environment as much as possible, right? If you're running in a much larger heap space than you have on production, well, then you're likely going to have your garbage collection run more frequently on production, and you're going to be slower there. And that's why, I mean, so I work for NewRelic, but I also think it's a great product, and that's why like something like NewRelic also fits into the performance picture. So that's something you can run on your production environment after you've done your development to see what's actually happening there. Yes? Mm-hmm.
And I was wondering if there's some way to disable some optimization from the GPU, because the question really is what it's doing wrong. It's the same values over and over in passes of these methods. And probably, I'm guessing there's some optimization done for the same parameters that are being passed, like any other values. Some optimizations are being cleaned. And that forces us to kind of hose with different sets of data and stuff like this. If there's a way to disable just that optimization, so we just pass on the same set of data over and over again.
Yes. Yeah, so the question was concern about using the same data for the method each time, and that causing optimizations that wouldn't necessarily be there in your production environment. And JMH, if you noticed on any of my JMH, let's see, so I have my variables 1 and 2 outside of the method. I'm not actually putting new pairs 3.1 and 2.2 in there. And JMH recommends that you do it this way, so your variables are outside of the method itself so that you won't run into that problem, and it won't just completely optimize for the 3.1 or the 2.2. So that'll help out a little bit. You can also check out the compiler modes of JMH. I don't know all of them there, but that does let you turn off specific features of the JIT, and like we did for the inlining. The question is, how does the JVM work with a multi-core environment? That's a good question. So I don't know. I don't work for hotspots, so I work kind of a level above it. So I don't know all of the details with exactly what optimizations are performed there for a multi-core environment. I don't know if anyone else has a good answer there. Yeah. So sorry. Anything else? All right, well, thank you all today. Oh, yeah.
Is there any tool that would, that would recommend to say these are the best practices and this must be followed to get the best outcome?
So the last point so the question was, are there any tools or best practices to ensure that you get the best optimizations possible? And the last point I made about just keeping your code simple and writing basic Java, I think is the best general principle to follow. Ultimately, if you need to do tuning, I mean, you can start getting into this stuff and thinking about things like, what are the size of my methods? If I have, that animal, how many instances, how many different types of animals do I have? These type of things can become important, but I think in general, you should really just write simple code, focus on that, and then when you do have a performance problem, know how to go figure out what it is. So. Yeah. So I believe, the question was, so there's really no tools out there that'll tell you whether or not your methods are being inlined or not. JIT watch actually will do that, but really what it's doing is just reading those log files. So you have to turn on the properties, spew out all that XML, and then either you go grepping away or you feed that into JIT watch and it'll tell you. So the information's there. You just have to kind of do a little bit of work. Anything else? All right, well, thank you all.